Well, good afternoon. My name is Mark Hilburger. Can you see my video okay?
Yes, we can see your
Okay,
slide.
great. Yeah, so as Athanu mentioned, I'm STMD's principal technologist for materials and structures. I am stationed at NASA Langley. And just a little bit of background on me, since most of you probably don't know me. I've been at NASA now for just over 21 years. My background is in structural mechanics with a focus primarily on structural stability of lightweight structures for aircraft and spacecraft. So the majority of my life prior to this position as principal technologist was fundamental research in that area. But anyway, I've been doing this job now as principal technologist for just over 2 years. It's quite an exciting time for NASA. Let's see. As you can imagine, with structures and materials, I cover a tremendous scope of work across all of our space technology areas. However, the hottest topic right now definitely is excavation and construction, and so it's definitely an exciting time to be involved in the planning for these missions moving forward over the next few decades. I'm excited to present to you a quick summary of our envisioned future related to E&C and how it supports the development of a sustainable lunar presence and space economy. But first, before I do that, I just want to thank Athanu and his team for organizing this workshop. I'm really looking forward to the interactions. And I also want to thank my NASA team of experts who really have done the real work in helping me pull all this material together. So, all right, so that's about all I wanted to say. I've got a lot to go through over the next few minutes, so carry on to the next slide. So first, I'll talk to you just briefly about what our envisioned future is for E&C and how it supports sustainable lunar presence. Then the bulk of my talk will be on capability needs and technology gaps. Originally, I was hoping that we would be able to present to you actual roadmaps and information on proposed demonstrations, but those are not yet authorized for us to present to the general public. So what I've done here is basically boiled it down to a list of some of the top capability needs and technology gaps related to various E&C technologies. And then finally, I have one slide on our current demonstration activities that we're planning. So next slide. So this is the envision future slide that we have developed for STMD. Basically outline a very high level capability needs for autonomous lunar excavation, construction, outfitting, where we're targeting landing pads, other surface structures, habitable buildings, and such, utilizing in situ resources. It's broken down into the several areas here. You start with the upper left. You see excavation for ISRU-based resource production. And really, when we talk about establishing a sustainable economy, it really revolves around being able to gather regolith and produce commodities. So for ISRU-based resource production, we're looking at technologies for site surveying, resource prospecting, require the mining of icy regolith, where we can extract hundreds to thousands of metric tons of commodities per year. So big challenges there. There's obviously a lot of interaction between myself and other PTs and system capability leads within NASA that are working in the areas of ISRU, autonomy, robotic systems, and so forth. Next, we have excavation for construction. A lot of similar technology needs, but obviously the mission focus is quite a bit different. all construction is going to require some type of surface preparation, which will include things like obstacle clearing, leveling, grading, compacting, trenching, and that sort of thing. We also need to be able to develop construction materials utilizing in situ resources. We're thinking somewhere between hundreds to thousands of metric tons of regolith-based feedstock for construction projects, tens to hundreds of metric tons of metals and binders as well. The third area in the center there is construction and outfitting. And I see landing pads, construction scaling up to human lander capable size pads. Unpressurized structure is then scaled to single and then multi-level pressurized habitats. We also have this area of outfitting, which is maybe not talked about quite as much, and that I'll talk a little bit more about later. But that's actually turning these structures into actual usable, functioning facilities. So we're talking about bringing in data cables, power cables, plumbing, air handling systems, etc. So how do we actually put install the systems into these structures? As we develop all these technologies, our final vision is to feed them together into a situation where we can provide for sustainable off-Earth living and working, much like what we are doing with the CLIPS landers. We see this evolving to a situation where we have commercially available excavation construction capabilities, where we can finally have some fully outfitted buildings supporting our permanent settlement and an economy. All the time looking towards Mars. So a lot of what we're doing here we see as being extensible to Mars, and so we always want to keep that in the back of our mind. All right, so that's a real brief introduction to our envisioned future. Next, I'm going to get into some more details on capability needs and gaps for these different areas. If you can go to the next slide, please. So first, I'll start with excavation for ISRU-based resource production. And so this is just a bulletized list of the types of capabilities that we're targeting. We're looking at regolith excavation, excavated and moved, an ultimate goal of something like 20,000 metric tons per year. These excavators and regolith movers are likely to need to travel over 1,000 kilometers per year, with repeated trafficking over a path of maybe over 3,000 times. It obviously depends on the concept of operations, how big the excavator is, and that sort of thing. We also are looking at recharging capabilities. We want these systems to be able to perform over a very long period of time, and obviously they're going to need to have the ability to recharge their batteries. We're looking at technologies for lunar survivability. We're targeting lifespans of around 5 years. Another thing and it's quite a bit different from what we call the white collar scientific rovers that you see on Mars, is these robotic assets are going to be working with very, very difficult conditions, literally digging deep into regolith, and so reliability and maintenance is going to be a big challenge for us. And we're looking at mean time before failure of 10 lunar days, but also have to come up with autonomous ways of not only doing all these actions, but also to be able to do autonomous maintenance and repair. So that's just a highlight of some of the capabilities for ISRU-based. If you go to the next slide, I have a list of gaps associated with this, including not only a system level gap of being able to actually excavate granular and hard icy regolith, but also sort of the subsystem level gaps, technology needs. including dust mitigation for actuators, sensors, seals, and joints, wear-resistant materials and wear characterization, understanding regolith flow and interaction with implements, long-life lubricants, motors, and avionics. The list goes on here. Sensors, power systems, autonomy, and robotics is a big area that we need to tackle, and again, autonomous repair. So that's ISRU-based resource production. And sorry if I'm going quickly. There's a lot of material here to get through in the 20 minutes. We can go on to the next slide. And here we switch gears to excavation for construction and site preparation. And as I mentioned earlier, there are a lot of similar capabilities as ISRU, but there's also some additional things that need to be considered, including site surveying for geotechnical and topography information, the ability to move bulk regolith, whether we want to build berms or we want to pile regolith on top of structures to provide radiation and micrometeorite protection. The ability to do autonomous site leveling, grading, and compaction, as well as rock removal, rock gathering, and trenching to bury, say, power lines and fluid lines, for example. Okay, so next slide. So a lot of the same gaps here as was seen for excavation for ISRU, but then there's some additional gaps associated with site preparation inspection. Essentially, the ability to, once you've manipulated your surface, to go back and actually inspect what you've done to make sure that it's sufficient before you perform your construction activities. In addition, developing implements for rock handling, grading, leveling, compaction, etc., are other areas that we need to do work. Okay, next slide, please. So now I'm going to spend some time talking about surface construction, and before I get into talking about the capabilities and gaps, I wanted to talk quickly about the different types of construction and put these technologies into context. So we like to think of the different classes of construction, starting with Class 1, which is similar to the International Space Station approach to construction, where we have pre-integrated modules that are built on Earth, tested prior to launch, and then delivered to a location and assembled into a larger system of modules. Obviously, there are some limitations here in that you're limited to your launch vehicle, payload shroud, and payload capability. But you do have benefits associated with everything being pre-integrated on the ground and tested. Class 2 is looking at prefabricated structures that can either be deployed or assembled in space. Much work has been done by NASA and some industry partners related to in-space assembly and inflatable habitats, for example. I think a lot of that is pretty well known. But it requires, again, some Earth manufacturing, but deployment and assembly is actually done on site. It does allow for partial integration and testing of subsystems, but there's still the potential for having to do additional integration and testing once things are deployed or assembled. Obviously, this allows you to potentially build much larger volumes, and so reduces your restrictions related to launch vehicle shroud size and payload mass, because you can potentially package these things into smaller volumes or bring them up in multiple pieces and assemble them on site. Also, there's the idea that Class 2 can be extended to not only include Earth-derived structures or pieces, but also include ISRU-derived parts once the ISRU construction capabilities are mature and available. And then finally, Class 3, where we're talking about manufacturing in situ derived from local resources, and is garnering obviously a lot of attention right now. I think is seen to be the holy grail of construction. There are some challenges associated with materials and processing that we're currently making very good progress on. It does require that we obviously provide for robotic manufacturing capabilities and requiring integration of subsystems, which is what outfitting really is getting at. But clearly, larger volumes are available with this construction technique, and we're no longer restricted to launch vehicle mass or size, other than the restrictions associated with actually launching the construction hardware itself. But other than that, really, it opens an entirely new design space for how we build off Earth. Okay, next slide. I've got a few more minutes and I just have a few more slides, so I think we're doing okay. So I'm going to go through Class 2 and Class 3 surface construction. And so for Class 2, obviously beyond just site preparation, we're looking at opportunities for horizontal construction, components of launch landing pads such as assembled blast shields, assembly of dust-free zones using paver systems, as well as vertical construction where you can see, for example, this arch-type structure, or Quonset hut, that is constructed autonomously out of a truss structure, and then some sort of paneling or maybe even a tarp system could be placed over it, and then regolith overburden placed on top as radiation micrometeorite protection. We're requiring supervised autonomy, system maintenance, repairability, as well as structural health monitoring. And then again, being able to autonomously inspect what we've built is potentially a very important part of this puzzle. Next slide. Okay, a bunch of gaps here. Again, deployment and assembly of discrete elements, being able to do this autonomously. Wiring harnesses and conduit and tubing really falls under the outfitting part of this E&C work. But of course, there's a gray area because when you're doing the construction, you need to be considering how you're going to do the outfitting. So there's some work that needs to be done in collaboration between those areas. And then some surface construction activities in Class 2 that are also shared with Class 3 associated with using ISRU-based construction, which are, say, the last 5 or 6 of those bullets associated with different types of material processing so that we can build pieces, parts that can then be used to assemble our structures. All right, I'll move on to the next slide. So here again, Class 3 shares a lot of the same capabilities as Class 2, but in addition to Class 2, you have the need for construction material preparation, and that's an area that is done in close collaboration with the ISRU group. We also have system maintenance and repairability. And then again, the V&V process inspection, not just inspecting what you've built, but inspecting the materials as you're processing them before and during the building process. So those are some of the highlights of Class 3 capability needs. And next slide, please. Okay, so some gaps. One of the biggest areas right now is a material deposition in a low pressure environment. So if you look to the right and you see some structures that the ICON group has developed using a 3D printing system. One of the biggest challenges is how do we deposit material in a low pressure environment and control porosity, get the as-built material properties as we would need them. Other gap areas include overhang support. So if we want to 3D print a structure that has some type of overhang, how do we do that? Again, material processing into construction feedstock, printer system motion dynamics, accuracy, and repeatability. So there again, we're working with autonomy and robotics to work on that gap area. And then a lot of the same types of gaps that I described earlier for Class 2, including how we do processing and microwave and laser sintering of regolith, for example, is another area of emphasis that our projects are working on. And one final slide, and I'm already 3 minutes over. Nope, I have 2 more slides. Here, I just want to talk about outfitting really quickly. We provide a definition so that people would have an understanding of what we mean by outfitting. And we've come up with this here: the process by which a structural system is transformed into a usable system by in situ installation of subsystems, as well as the associated planning and preparation required for the process. So the subsystems that we're talking about include power, lighting, HVAC, water, hydraulics, etc., data communications, as well as things like windows and hatches and interior furnishings. So everything that you need to make a house a home, essentially. Next slide, please. So outfitting isn't nearly as far along as some of the other areas, but they've identified really 3 high-level gap areas, including power and data, cable management. So that revolves around installing, securing these cables, as well as coefficient of thermal expansion management and protection against micrometeor and impact, as well as radiation. Piping and tubing, line management have the same challenges, as well as considering repairs when wet, and how do you deal with spill management. And then the final gap would be penetration management. If you think about bringing outside lines into your house, you're going to have to have some sort of opening, which introduces a design discontinuity and potential failure site. So how do we deal with these penetrations? How we seal these penetrations and verify that we've sealed them properly. Okay, one more slide and then I promise I'll be done. So the final slide here is a slide on the different demonstrations that we currently have planning across the LSII. This is the one slide that's been approved for us to share publicly. And you can see the last line there is for construction, excavation and construction. So we do have some early demonstration opportunities, including the ISRU pilot excavator and the Lunar surface construction demo. We're just now in formulation of these demonstrations, and there's a lot more work to be done. So I can't really comment on what these demonstrations are going to entail at this point, but certainly they're going to be focusing on a lot of the the early sort of fundamental capabilities needed for excavation and construction. There's also some opportunities for us to leverage other demonstrations, including some extreme environments demonstrations on lunar materials. So when we talk about surviving lunar night, we have opportunities to potentially leverage some of those demos, as well as working with surface power to demonstrate wireless recharging, and also ISRU, as we're obviously working with them to actually excavate materials for them to process. So that's pretty much it. Sorry I went over, but I think hopefully that gives you a good snapshot of what we're looking at, and where we want to be going over the next decade or two. Again, I appreciate you all tuning into this workshop. I'm looking forward to all the fruitful interactions that I know are going to come. So thanks very much.